Look at the sea. The water moves in endless waves. A gust of wind makes new ripples. Your voice makes waves in the air. Light travels in waves. A radio signal spreads like an invisible ripple across a vast pond. All of these waves carry information. They tell us where a sound originated. They tell us what color we see. They carry songs and conversations across continents. We call this kind of signal analog. Analog is an analogy, a reflection of the real world. An analog signal changes in a smooth, continuous way. The wave can be tall. The wave can be short. The wave can be fast. The wave can be slow. It can take any value between its lowest and highest points. No sudden jumps, no missing pieces. It is an unbroken flow, a mirror of the world. For most of human history, information was analog. From grooves on a wax cylinder to changing shadows on a sundial. It was as continuous as time itself. Now think of something different. Think of a simple light switch. It has only two states. It is off. It is on. There is no in-between. A bit is exactly like that switch. It can be a 0. It can be a 1. Digital systems are built from this simple duality. A digital signal does not flow smoothly like a wave. It moves in distinct steps or levels. It is not continuous. It is discrete. Your smartphone, your laptop, your television, they speak the digital language. They translate the rich analog world into a long series of on or off bits. The fundamental question, how do we get from one to the other? How do we transform infinite wave complexity into countable bits? This translation is at the heart of our technological world. It lets us capture a sunset in a photograph. It lets us record a symphony on a compact disc. It lets us have a conversation across the planet. We invented converters to bridge the gap. This journey, from continuous to discrete, from waves to bits, is how we learned to tame information itself. Let's delve deeper into the analog world. The defining characteristic of an analog signal is its continuity. Imagine drawing a line on a piece of paper without ever lifting your pen. It can curve up and down, change direction, vary in thickness, yet remains unbroken. A perfect metaphor for an analog signal. When you speak, the sound pressure waves your vocal cords create are analog. They rise and fall in a fluid, uninterrupted pattern. The voltage coming out of a microphone that captures your voice is also an analog signal, a fluctuating electrical current that perfectly mimics the shape of the sound wave. A direct, physical translation. This directness is both analog's greatest strength and its vulnerability. Consider a vinyl record. A needle travels through a physical groove etched into the plastic. Those tiny wiggles are a direct physical analog of the original sound waves. The needle vibrates, and those vibrations are amplified to recreate the music. There is an elegant simplicity to this process. It captures a richness and warmth many feel is lost in digital translation, more organic, more present, a direct imprint of the performance, with subtle nuances and imperfections. However, this physical nature makes analog information fragile. Each play slightly wears the groove. Dust, scratches, static introduce hiss and pops not in the original. Signals degrade, and each copy grows noisier. The information is not stable. In stark contrast to analog's smooth continuity, the digital realm is discrete. Like a staircase you can stand on, but never between. This difference changes how information is handled. Digital does not recreate a perfect continuous signal. It measures at intervals and assigns numbers. Infinite complexity becomes a finite set of numbers, represented in a special language. Binary. Binary uses only two symbols, 0 and 1. A single 0 or 1 is a bit. Bits combine into strings to represent any number, letter, instruction. 0, 0, 1, 1, 2, 10, 3, 11. Each position is a power of 2. Binary is the universal alphabet of digital machines. Once information becomes zeros and ones, it is robust and versatile. Copying a digital file simply reads a sequence of numbers and writes the exact same sequence. The copy is a perfect identical clone, even the millionth. Analog copies degrade, digital doesn't. Because digital is math, we compress to save space and add error correction, so devices detect and fix transmission errors, yielding perfect or gone results. Converting a smooth analog wave into digital numbers is a two-step dance. Sampling and quantization, the bridge between worlds. Sampling measures the signal at lightning-fast intervals. Like measuring a hill's height at every foot. More samples, more accurate shape. In audio, an ADC samples CD quality at 44,100 times per second to capture the ear's full range. Too low, and you lose high-frequency detail, sounding muffled. Too few snapshots can't faithfully reconstruct the wave. After sampling comes quantization, assigning each measurement to a level, rounding like inches on a ruler, introducing a tiny error. Bit depth sets the number of levels. 16-bit audio has 65,536 levels. Errors are so small, they're usually inaudible. Lower bit depth increases rounding error, adding hiss or reducing dynamics. Digital quality depends on how often you sample and how many levels you choose. No system is perfect. Both analog and digital have strengths and limits. Digital's immunity to degradation revolutionized archiving and distribution, easy to search, edit, and transmit. Digital is efficient, versatile, and enables powerful processing. In the end, we live in a hybrid reality, perceiving waves, sharing bits, the continuous and the discrete dancing through our modern world.